we have this matrix A, x equal to B. So I solved for x in order n cube. Well, maybe after some time, maybe tomorrow, I get another B. A is same, but I get B prime. Then I can again solve for x, but that will again take order n cube. So what do I do? If the matrix is used very often, this equation, then you can compute A inverse beforehand. Compute A inverse. And then if you know A inverse, then x equal to A inverse times B, and this will take order n squared. Right? This is matrix multiplication is each time n guys works with order n squared. By the way, you may think that this is no big gain, but matrices could be order like 10,000 by 10,000. Okay, so these are 10,000 squared is huge, and 10,000 cube is even bigger. Okay, so if you are working with all this network optimization, you get these matrices, and number of computers are like huge, millions. So LU decomposition. So it is A inverse is obtained by LU decomposition. Okay, so that's what I'm going to describe now. So the theorem is any matrix A can be written as product of three matrices P, L, U. So P is called permutation matrix. P is permutation matrix. U is upper diagonal matrix, which I just showed you in the earlier discussion. Upper triangular matrix. Okay. So the matrix where all the entries below the diagonal are zeros. Okay, upper triangular. L is a lower triangular matrix, but it's a lower triangular, except one difference, that all the diagonals are ones. All the diagonals are one. Okay, and these are non-zero, and all the entries above the diagonal are zeros. Okay, so this is lower triangular matrix. Okay. So it's a theorem. Okay, I'm not proving it. Okay, you can see some advanced book to see the proof. Okay, so okay, that's a statement. Okay, so PLU, and if I know this PLU, well, okay, then you can compute X. In fact, you don't have to find inverse. If you know LU, then we can compute X quite easily. So I need to solve X equal to B, no? This equation. So what do you do first? I put P inverse. Take this P and take it to the right hand side, which is P inverse B. So this is order n squared. So the B prime. After this, what will I do? I solve for L y equal to B prime. B prime is known, L is known. I can solve for y. Okay, this will be done by back substitution. Order n squared. Okay. After I found y, then I can find x. You can see, compare these two equations. What is x? Ux equal to y. Right? I substitute ux by y, so that ux equal to y. So x equal to u inverse. Well, basically, don't do inverse, but you just use back substitution to find x. Okay, so this is again order n squared. So order n squared, 3 times order n squared, which is much smaller compared to order n cube for Gauss elimination. Okay. Or you can also compute A inverse. Okay, how will you do A inverse? Also quite easy. So replace B by one vector where all the entries are 0 except one of them is 1, which is the ith row. Okay, and I solve for it. So the solution for this is xi. Okay, you can use LU decomposition for computing xi in order n cube. Then you do it for all i's, I equal to 0 to n minus 1. And once I know this x0, x1, x2, x3, I arrange them in a row. So These are all columns. Huh? These are column, 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 column. So this is a matrix, and this matrix is A inverse. You can check yourself that this indeed is a A inverse matrix. So I can multiply this by from the left and check whether I get identity. Okay. So I will not show you, but it's easy to see. So that's A inverse matrix. Let's do some examples. So I have one matrix, 3 by 3 matrix, but you represent the matrix like that. Okay. So this is 1, 1, 0, 3, 2, 1, 0, 1, 3. So you put the first row, then 3, 2, 1, second row, and third row. So A is part of NumPy. So A and P are A, and like that. B is a vector. So it's a 3, 10, and 11. Now I want to find X which satisfies this equation, Ax equal to B. Okay, so I'm going to import this linear algebra library, linLG, from SciPy module. Okay, and just say X equal to linLJ, solve. Two arguments are A and B, and X is here. Okay, in fact, we solved this problem some time back. Okay, so that's what we got. 1, 2, 3. That was the answer. Okay. So Python offers these functions. You don't need to write your own Gauss elimination scheme. It works. You can also compute for this matrix A. What is LU? We just say lin ALG, LU, an argument is A. So this will give you, well, the left side is PLU. Okay, just put these three arguments, PLU equal to. So P will be permutation matrix. This is 0. So basically, you can see that each row has only 1, 1, and each column has only 1, 1. Okay. So this is, as I told you, that if any of the diagonal is 0, then we need to swap. If diagonal is 0, then Gauss elimination does not work. So Python does some swapping. Anyway, so this is P permutation matrix. This is a lower diagonal. You can see that all the diagonal elements are 1. And this upper diagonal, where all the entries below the diagonal are 0. Okay. So these are useful functions, and you need to know this. Okay. So in the exam, we may just ask you this. Okay. Now there are some special kind of matrices which we encountered before. Okay. So in splines we had triangle matrix. So triangle matrix are, so diagonal entries are non-zero, one above the diagonal and one below the diagonal. Rest all are zeros. Okay, so this is called tridiagonal matrix. So it is not only, it has 3 diagonals. Okay, 3 diagonal means one above the diagonal and below the diagonal. So this is my matrix A. So we write another matrix. Okay, so in this matrix AB, the diagonals are in the center. Diagonals are this 1, 2, 3. 1, 2, 3. The diagonal is here. The upper diagonal is here, 1, 1. But there should be one entry here, right? The extension, you just go one above. And this one, you go one below. Okay. So this dot, you can see my pen. This dot you put by dash. Okay, this dash. So this dash is unknown. This is not there. But I want to write into the matrix. So I need to put some entry, which Python will ignore. Okay. We need to put a number, in fact. We can't put a dash. We need to put a number. So that is some arbitrary number in 1, 1, these two. Below 1 is 3, 1. This 3, 1. 3, 1. But this guy is arbitrary, and you just put some arbitrary number there. So that is matrix AB. Okay, so let's put that. So AB is so I put for the dash zeros. I replace this dash by 0. So 0, 1, 1. These three guys. Then 1, 2, 3, 1, 2, 3. Then 3, 1, 0. B, I'm solving for some stuff, some vector B, and I'm looking for, of course, X. So function I'm going to invoke is solve bandit. Okay, solve bandit has arguments. You pass this one, AB. You don't solve, put A. Okay, A is I'm giving a simple example, 3 by 3, but in general it could be like 1000 by 1000 matrix. Okay, but this matrix will be only 3 rows. Okay, so it will be, this will be 1000, 3 by 1000 matrix. And a lot of it will be automated. You will not be putting by hand. So AB is here, B is this vector, and this is telling you that one above and one below diagonals are non-zero. So this one is below and this above diagonal. This is 1, 1 is that. This function also works for, let's say, 2 diagonals above and 2 diagonals below are non-zero. Okay, that will work. And answer is, of course, 1, 2, 3. So this is, in fact, it's the same problem which I've been doing it. Okay, so we solved earlier with Gauss elimination. Then I showed you by Python function, and I'm again showing you the same thing using for banded matrix. Okay, so I think this is what I will do for part 1 of linear algebra, which involves solving algebraic equations.